Solution of linear equations is a big part of applied mathematics. Solution of linear equations is not only necessary in linear algebra, but also you will see later on that solution of linear equation forms the basis for the numerical solution of ordinary as well as partial differential equations. In fact, more you get into numerical methods, you will see that more and more you need efficient solvers for solving large systems of linear equations. In your high school, you must have studied Cramer's rule for solution of linear equations. Now, Cramer's rule is very nice until you have large number of equations. Up to 3 equations, 3 unknown case, Cramer's rule is absolutely fine. But as soon as you go beyond that, using Cramer's rule or anything, for instance, where we use determinant, is not very efficient. There are many different methods for solving linear equations, and the first one that we will learn now is the Gaussian elimination. Gaussian elimination, as you will see, is a 2-step procedure. Here, the goal is to decouple the coupled equations. And once we can decouple the coupled equation, we can solve serially one unknown from one equation. So this 2-step procedure consists of first step, that is the decoupling of equation, and we call that forward elimination. And then comes the second step, where we solve one unknown after another serially, and that is something we call back substitution. So let's see how it works. Consider a set of linear equations a11x1 plus a12x2 plus a13x3 etc. up to a1n xn equals b1, that is equation 1. Similarly, the second equation is a21x1 plus a22x2 plus all the way up to a2n xn equals b2. And similarly, we can go on up to n equations where we have an1x1 plus an2x2 up to ann xn equals bn. We can write this in shorthand as the summation between j equal to 1 to n aij xj equals bi, and we write this for I equal to 1, 2, 3, 4 up to n. For each I, we get one equation. Now, this n equation we used to solve for the unknowns x1, x2, x3 up to xn. And we assume at this point that this is a very well behaved system. That means this system has unique solution. There is no major problem with the system of equations itself. So the problem of solving this is that the equations are coupled really. So which means that every equation has more than one unknown. We know that if we have a situation where each equation has only one unknown, we can solve it easily. But now that every equation has more than one unknown, we have to do something. So essentially, any method that we use, the goal is to decouple. And here we will talk about this elimination technique, Gaussian elimination in particular, where the primary idea is to replace an equation with a linear combination of several equations, and this will decouple the equation. Now this may look slightly complicated, but this is exactly what you did in your high school when you solved two equations and eliminated one unknown from one equation. This is exactly what you did. So when we try to apply the elimination technique, there are fundamentally two different eliminations that you will see. One elimination goes to complete decoupling, and complete decoupling means at the end you will have one unknown, one equation type system, and that is something we call Gauss-Jordan. So at the end of elimination, if you think from this set of equation, the set of equation only have the elements a11, a22, a33 up to an, other elements will go down to 0. And that is something is Gauss-Jordan elimination. The other type of elimination that we are really interested about, that is the Gaussian elimination. In Gaussian elimination, we don't go for a complete decoupling as in Gauss-Jordan. Rather, we create a system where the nth equation will have only one unknown, that is xn. n minus 1th equation will have two unknowns, that is xn and xn minus 1, etc. And this is how we'll go. Now you see that in this form, even though the n minus 1th equation has two unknowns, before we come to n minus 1th equation, we can solve xn from the nth equation. And that is how the n minus 1th equation, for all practical purpose, we can say that it has only one unknown, even though it is not. So this is the difference between Gauss-Jordan and Gaussian elimination. Gauss-Jordan requires much more calculation really. So that is why we prefer Gaussian elimination. Gauss-Jordan is necessary for other purposes, such as finding inverse of a matrix or going deeper into linear algebra and learning more about the nature of matrix itself. Sometimes Gauss-Jordan is necessary. But for the solution of linear equation, Gaussian elimination should be good enough, where we have this sort of a structure. Nth equation has one unknown, n minus 1th equation has two unknown, n minus 2th equation has three unknowns, so on and so forth. So let's see how it works with a simple system. Think about a situation where we have two equations, two unknown. You have solved this many times since your school days, and the way you have solved in your school, we'll do exactly the same thing here. So let's see what you did. First, we identify this element, which is the corner of the first equation, that is this 3, as the pivot. And then I do linear operation. My linear operation is that this equation 2, I'll bring a new equation 2. I'll replace the old equation 2 with the old equation 2 plus minus 4 by 3 multiplied by equation 1. And how come this minus 4 by 3 coming? This minus 4 by 3 coming, here 3 is the pivot and 4 is the coefficient of x, that is whatever it is that is just below the pivot. So that is coming here. 3 is the pivot, 4 is the coefficient of x in equation 2 with a minus sign. And I might multiply that minus 4 by 3 with equation 1, I add with equation 2. Once I do that, you understand that in my new equation 2, the coefficient of x will be 0. So what is going to happen here is that I am getting a new equation 2, that is 7 by 3 y equals 7 by 3. Nothing happens in equation 1, but I have a new equation 2. So please verify the operation we are doing here. We are not doing anything in equation 1. Equation 1 is multiplied by minus 4 by 3. That does not mean equation 1 is changing. This multiplied equation 1 is added to the old equation 2 to give me the new equation 2. So my new equation 2 is 7 by 3 y equals 7 by 3. So now you see that one unknown in equation 2, that is y, and then two unknowns in equation 1, that is x and y. And this particular step sorts of, it decouples the equation. So we call this step forward elimination. This is the first step of Gaussian elimination. Now in second step, we will call this second step as back substitution. And in back substitution, we will do precisely two things. One is that solution of equation 2 for y, which is very simple because equation 2 only has y. There is no x there. And then once we know y, we will solve equation 1 for x. So what we do here is that equation 2, I multiply equation 2 with 3 by 7 and then I add 0 of equation 1. That means that I don't do anything with equation 1 really. What I do, I take equation 2 and I multiply equation 2 with 3 by 7. Once I multiply with 3 by 7, my equation 2 comes to y equal to 1. Equation 1, nothing happens here. 3x plus 2y equal to 5, it still remains. But now that I know y equals 1, I can solve x from equation 1. So it's very simple now. X equal to 5 minus 2y by 3, and y I know that already that it is 1. So 5 minus 2 by 3 equals 1. So my solution is now complete. Of course, this is a very simple example. Nevertheless, it tells us all the steps of Gaussian elimination. The first takeaway from this exercise is that a pivot, that means here you see that the 3 was my pivot, and in my elimination process this pivot is coming below 4. If the pivot is 0, then my solution procedure falls flat. So a pivot cannot be 0. This is the first idea of Gaussian elimination. We are always dividing by pivots, so a pivot cannot be 0. Not at the initial state and also not anytime during the operation. This is very important because we have control over initial state. We don't know what will happen during the operation, but we must take a matrix for which the pivot will not be 0 during the operation. For any non-singular matrix, of course, this will work, and we have a check of this and we will talk about it later. The other point is that we see that Gaussian elimination, we can now segregate it in two parts: forward elimination and back substitution. Now you go for a slightly more complicated situation where we have a 3 by 3 system, 3 equations, 3 unknown. Here our goal is first to take this pivot 2, and then we want to bring 0 in place of 4, we want to bring 0 in place of 3. So what are we going to do now is we take equation 2, the new equation 2 is equal to old equation 2 plus minus 4 by 2 multiplied by equation 1. This 2 is the pivot and 4 is the coefficient of x1 in equation 2. Similarly, in equation 3, our new equation 3 equals minus 3 by 2 multiplied by equation 1 plus old equation 3. And here also you can see that 2 is the pivot and 3 is the coefficient of x1 in equation 3. Once I carry out this operation, I have eliminated x1 from both equation 2 and equation 3. So now equation 2 and equation 3, they have only x2 and x3. So what I'm going to do now, I'll use this 4. This is my new pivot now. And I'll eliminate this 5 by 2 from the equation 3. So what I do is, with this pivot 4, I write this equation 3 new equal to old equation 3 plus equation 2 multiplied by minus 5 by 8, And I hope you understand that how this minus 5 by 8 is coming. This is coming from minus 5 by 2 divided by the pivot, that is 4. So this is how this minus 5 by 8 is coming. Once I do this operation, what I have is the coefficient of x2 in equation 3 is now 0. So equation 3 now has only x3. Equation 2 has x2 and x3. And equation 1 has x1, x2 and x3. So in some sense, it is by and large decoupled. As much decoupling is needed for Gaussian elimination. And this is where we end the forward elimination part. Now we have to go for back substitution. In back substitution, I first calculate x3 from equation 3, because equation 3 only has one unknown. Then I go to equation 2. In equation 2, I have x2 and x3, but now I know x3, so I can calculate x2 from equation 2. And now I can go to equation 1 and calculate x1. Equation 1 of course has x1, x2 and x3, but x2 I already know from here and x3 I also know from here. So I can calculate x1 from equation 1. So now you see that we talked a lot about linear algebra and matrix and different operations of matrix, but we pretty much discussed Gaussian elimination without any reference to matrix. The technique, of course, we can write it in matrix form and we will do it now, but the utility of writing in matrix form may not be clear now. You can learn Gaussian elimination without knowing anything at all about matrices and different operations of matrices, but going deeper into it and improving it or comparing with other methods requires knowledge of matrices, and we'll see that later. But right now let's first see that how we can write this technique in terms of matrices. So we take this simple case that we were discussing initially, 3x plus 2y equals 5 and 4x plus 5y equals 9. This system I can write as an Ax equal to b system, where A is the coefficient matrix, that is 3, 4, 2, 5, and B is the column vector, that is 5, 9. X is a vector xy, and then I can write this is a matrix vector multiplication. A matrix x vector, if we multiply, we get a B vector. Just like we write coefficient matrix A, we can similarly write something we call augmented matrix, and augmented matrix takes care of both A and the column vector B. We show a dot here between the coefficient part and the column vector B part, just to segregate this A matrix and B vector part. The dots do not have any mathematical implications at all. So now we take this and we go with Gaussian elimination. So in Gaussian elimination now we can use simply the augmented matrix, and in this augmented matrix we carry out the forward elimination. In forward elimination we don't do anything in the row really. We have to replace each row with a linear combination of other rows, but row 1 we replace with row 1. So essentially we don't do anything in row 1. Row 2 is of course replaced, that we have seen before. This will be minus 4 by 3 of row 1 plus 1 multiplied by row 2, and this is something we call elementary operation, and we will come to it later on. Once we do so, we get a matrix that is 3, 2, 5, which is the first row, that remains same. So please note that when we are now talking about row, the 5 is also coming in the row. It's not just the coefficient matrix, we are talking in terms of augmented matrix. So the first row is 3 to 5 and that remains same. The second row is now changed, 0, 7 by 3, 7 by 3. And this pretty much completes the forward elimination part. We can now go to the back substitution, and for the back substitution, once again we can simply break down in the equation here. You can continue doing elementary operation in this matrix and divide the second row 7 by 3, which will give you y equal to 1, and then take this y equal to 1 and come on to this x, finding x from equation 1, and then we'll get x equal to 1. So this is how we can write in matrix form. Although at this point we can see that it does not give us any advantage of thinking in form of matrix. Absolutely, we can solve equations using Gaussian elimination without any reference to matrix at all. So now our goal is to generalize this procedure. For generalization, what we mean is that we talked about 2 by 2 system, we talked about 3 by 3 systems, but for any practical applications, our systems will have many more equations and many more unknowns. In fact, it could be very, very large, hundreds, thousands, even millions of equations. In these days, people are solving billions of equations, trillions of equations. So we may not have to go there, but at least we have to go up to tens of equations or hundreds of equations. At the end of this course, you will probably solve thousands of equations. And this technique that we have now seen here, how can we extend this to a situation for n equation, n unknown? That sort of generalization we'll do in our next lecture. For now, you try Gaussian elimination. Don't write a computer program now. There are many computer programs available here and there for Gaussian elimination. Don't get into that trap. You follow all the steps and solve this set of equations using Gaussian elimination, using simply pen and paper calculation. Do not use a computer program now. It's very important to understand that how the algorithm works. It's very important to understand that what are the problem. It's also important to understand that where it takes more time, how many number of calculations it takes before you can actually sit down in front of a computer and write the code. So that's all for now. Thank you, and I'll see you in next class.